Good morning, everyone. Myself, Darshan BD, Assistant Professor, Department of ECE, SJBIT. So these are some textbooks. So we are discussing the Module 2 content. So you know that the Module 2 we are having oscillators and operation amplifiers. Consider the Wein bridge oscillator. In the Wein bridge oscillator, here output of the amplifier is fed back to the Wein bridge feedback circuit. Here the RC ladder, this network provides the phase shift with varies with the frequency. The input signal is applied to A and B. A and B are the input point, while the output is taken from C and D. So you can observe in the figure, so this A and B are the inputs, the C and D points are the output. We are going to apply input to the bridge. This is in the form of bridge, which consists of resistor and the capacitor. The phase shift produced by this network will be exactly 0. That is, the input and output signals will be in phase. When you are going to consider, that is, the phase shift is produced means we can consider as an out of phase signal, since here the output are produced from the Wein bridge oscillator. The phase shift produced from this network will be exactly 0. So if we connect the network to an amplifier producing a 0-degree phase shift, which has a sufficient gain to overcome the losses of Wein bridge oscillator, Wein bridge oscillation will result. Consider that the conditions for the oscillation in the Wein bridge oscillator are: op amp acts as an amplifier, produce 180-degree phase shift. Bridge network as a feedback network, produce another 180-degree phase shift. As a result, the phase shift is around entire loop is 360 degree. This is one of the conditions to get the sustained oscillation. Second one is A is the gain of the amplifier and beta is the gain of the feedback circuit. Then loop gain is given by A into beta is equal to 1. In Wein bridge, resistor R1 and R2 and capacitors C1 and C2 form the frequency adjustment element. Here we can consider, so the R1 and R2, so this R1, this is R2, then C1 and C2, considered as the frequency adjustment elements. But R3 and R4 forms a path for the feedback path, because so since only we are going to consider R1, C1, R2, C2 means we cannot form a bridge. So this R3 and R4 provides the path for feedback. In most cases, we are going to use the same capacitor value. C1 is equal to C2 and the resistor also R1 is equal to R2. Hence the minimum amplifier gain will be 3. That is, beta is equal to 1 by 3. The minimum amplifier gain required to sustain oscillation is given by, you can consider that AV, voltage gain is equation is 1 plus C1 by C2 plus R2 by R1. So considering this, we can see that, so that when you are going to vary that C1, C2, R1 and R2 value, we can get the different the gain also. As I mentioned, the minimum amplifier gain required to sustained oscillation is AV is 1 plus C1 divided by C2 plus R2 divided by R1. In most cases, we are going to use the same capacitor value, that is C1 is equal to C2 and R1 is equal to R2. So hence the minimum amplifier gain will be 3. As we know that the gain, minimum amplifier gain is 3, because C1 is equal to C2, so that this value becomes 1 in the formula. R2 divided by R1, this is also 1, so that AV is 1 plus 1 plus 1, we are going to get 3. So at one particular frequency, the input and output signals will be in phase. In phase means that phase shift produced by net circuit will be exactly 0 or 360 degrees, and at which the values of the resistance and capacitance and capacitive reactance will become equal, producing maximum output voltage, because we are going to consider that the capacitor and resistor value at some point we are going to get a 0 phase shift. So that particular resistor and the capacitor reactance will become equal. So in that time, the frequency of oscillations can be determined considering R1 and R2 is equal, C1 and C2 are equal. The frequency at which the phase shift will be 0, you can consider that the frequency is 1 divided by 2 pi square root of C1, C2 and R1 and R2 value. When we are going to use the common resistance value, R1 is equal to R2 and C1 is equal to C2, the frequency at which the phase shift will be 0, then the frequency equation becomes F is 1 by 2 pi square root of C square into R square. So that is square root and square will cancel, so that the final equation is F is equal to 1 divided by 2 pi C R C. So where R is equal to R1 is equal to R2 and C equal to C1 is equal to C2. So we can use that. We can use the different the capacitor and the different resistance value, but we have to simplify this equation. We are going to consider the common resistance and capacitor value. So you can design the resistor and capacitor value for different the frequencies. So we can keep the capacitor constant and we can vary that the resistance with respect to that. So instead of varying only one resistor, the proportionally we are going to vary the two resistance value means, so that we can keep that resistance value the same. Okay, so therefore that adjusting the parameters will become simple. So when you are going to vary that 10 kilo, I want to vary that. So that instead of varying a one register, we can vary and we can split that whatever the value is there. So we can split and we can equally divide it into two resistors. So this is the Wein bridge oscillator. So consider an example. An Wein bridge oscillator based on the operational amplifier. If the capacitor value C1 is equal to C2 is 100 nanofarad, determine the output frequency produced by this arrangement when resistance values of R1 is equal to R2 is 1 kilo ohm and R1 is equal to R2 is 6 kilo ohm. For two different resistance value, so we have to find out the frequencies. So considering this is the diagram, so we know that this is the bridge form. That this is the bridge only, then the Wein bridge. Okay, so we are written in this form. So we are considering that. So this is the C and D. We are going to consider the output. So we are considering that the part in the solution, we are considering the R1 and R2 is equal to 1 kilo ohm. We have to consider the resistance value is 1 kilo ohm. Then R is equal to R1 is equal to R1, so that we can consider R value. So F naught is 1 divided by 2 pi into RC. R value is 1 kilo ohm. C value is 100 nanofarad. Nano is 10 power minus 9. So that the frequency is 1.59 the kilowatts. Similar way, when we are going to vary the resistance value. So in the first case, we are considering the R1 and R2 is equal to 1 kilo ohm. Similar way, the second one, the R1 and R2 is equal to consider 6 kilo ohm. So that the formula will be same that. So we can consider F is equal to 1 by 2 pi RC. We can substitute the instead of 1 kilo ohm, we can substitute 6 kilo ohm. So that the frequency is 265 hertz. You can observe that the resistance value is 1 kilo ohm, we got frequency is 1.59 kilohertz. If the resistance is increases to 6 kilo ohm, we got 265 hertz. So we can come to know that when you are going to increase the resistance value, the frequency is reduces. So we have to reduce the resistance value so that we will get the maximum frequency output. Consider the multivibrator. So there are many occasions when we require a square wave output from an oscillator rather than the sine wave output. So in the previous topic we discussed that Wein bridge oscillator, the output is the sine wave. Suppose we require a square wave rather than the sine wave, we go for the multivibrator. Multivibrator are a family of oscillator circuit that produce output waveform consisting of one or more rectangular pulses. A multivibrator is also an electronic device that produce non-sinusoidal waveform that generate non-sinusoidal waveform like a square wave, rectangular wave, a triangle wave, sawtooth wave. It can be constructed using two-stage RC coupled amplifier with a positive feedback from the output of one amplifier to the input to the other one. So considering the principle of operation, the switching circuit has two-stage amplifier with output of one fed back to the input to the other. Okay, so like that also we can consider. The term multivibrator simply originates from the fact that this type of waveform is rich in harmonics, that is multiple vibrations. Multivibrators use regenerative, that is positive feedback. The active devices the present within the oscillator circuit being operated as a switches, being alternately cut off and driven into saturation. The mainly two types of multivibrators, we can call it as principal type of multivibrators are astable multivibrator, monostable multivibrator and the bistable multivibrator. Astable multivibrator, this circuit consider the principal type of multivibrator, astable multivibrator that provide a continuous train of pulses, it is free running multivibrator. Monostable multivibrator that produce a single output pulse. They have one more stable state and are sometimes also referred as one shot. Bistable multivibrator that have two stable states and require a trigger pulse or a control signals to change from one state to another state. This is the main principal types of multivibrator. Consider single stage astable oscillator. An astable oscillator that produces a square wave output can be built using op-amp. The circuit employs a positive feedback with a component with the output fed back to the non-inverting input via the potential divider formed by R1 and R2. A simple form of astable oscillator produces a square wave output. It can be built using the operational amplifier you can observe in the figure. The circuit can make a very simple square wave source with a frequency that can be made adjustable by replacing the R with a variable R present resistor. Consider a capacitor C initially uncharged. So uncharged means you can observe that this capacitor voltage is 0. Uncharged voltage, that capacitor voltage we are going to apply to this the inverting terminal of operational amplifier. When you are going to consider that the output, that we are going to take the input of the non-inverting from the R1 and R2 register. The capacitor is initially uncharged, means voltage is 0. The output of the inverting is slightly less than the voltage at the non-inverting terminal. This means the positive terminal is more than the negative, so that the output will rise rapidly to positive, and the voltage at the inverting input will begin to rise exponentially as the capacitor is charged through resistor R. We can consider this from the operational amplifier. Non-inverting terminal is dominating the inverting terminal, means we are going to get the output, the positive output, because V2, V0 is V2 minus V1. V2 is the non-inverting terminal, V1 is inverting terminal. Then at that time the capacitor is charged through R, resistor R. Once the capacitor is charged fully, the voltage at the inverting input will reach to the value that causes the voltage at the inverting input is exceeds or more than the present input at the non-inverting terminal. Now the non-inverting terminal is less than the inverting terminal. Inverting terminal is dominating. Then the V0 is V2 minus V1, so that the output is negative. So the output voltage will rapidly falls to negative, minus VCC. The capacitor C will then start to charge in other direction, and the voltage at the inverting input will become the fall exponentially. So in the whenever the output is positive, so we are going to consider the capacitor is charging in one direction, this is positive direction. Whenever the capacitor is negative, it is going to charge in a opposite direction. We can consider it a fall exponential. Eventually the voltage at the inverting input will have reached a value that causes the voltage at the inverting input to be less than that present at the non-inverting input. At this point the output voltage will rise rapidly to positive VCC. Once again the cycle will continuously indefinitely, so that it is continuous the process. To consider the upper threshold voltage, that is the maximum positive value for the voltage at the inverting input will be given by VUT, means the upper threshold voltage is equal to VCC into R2 divided by R1 plus R2. The lower threshold voltage, that is the maximum negative value for the voltage at the inverting input, will be given by VLT. VLT is lower threshold voltage, is minus VCC into R2 divided by R1 plus R2. Finally, the time for one complete cycle of the output waveform produced by the astable oscillator is given by, so T is equal to 2CR ln of 1 plus 2 R2 divided by R1.